All right, let's start looking at elliptic curves over finite fields. So this is the foundation of elliptic curve cryptography. Well, we're going to be working in a program called Sage today, which is just Python plus a little bit of extra stuff. So most of the notation is going to be very familiar. There's just a handful of things that you'll need to work with elliptic curves over finite fields in Sage. But mostly the notation should feel very familiar as Sage is built basically on top of Python. So announcements, again, everything's in MyOpenMath. Make sure you are working on stuff in MyOpenMath. If you don't have everything done that you want to have done, again, come to class. Basically, class is flipped for the rest of the semester, so come to class during our regularly scheduled time and work on whatever you need to get to the grade that you want. Okay. All right. So last time we talked about elliptic curves, and I talked about addition of points on elliptic curves, and I claimed that forms a group. The set of points on an elliptic curve with that operation of addition forms a group. And that is true. The one thing that I left out was what is the identity element? And so we need to talk about the additive identity. And that's going to be a special point that we call the point at infinity. And that's a special point that lies on every single vertical line. So as a reminder, if we're just talking about general groups for a second, if G is in the group G, capital G, then the identity element is that special element E, such that E plus G is just equal to G. It's 0 in the integers and the rational numbers and the real numbers. It's 0 for those groups under addition. It's 1 for instance, the real numbers under minus 0 under multiplication. And so it's that special element that basically doesn't do anything when you do the group operation with that element. Okay, so for us, let's think back to elliptic curves for a second and remind ourselves of how addition is defined. We are going to be looking at an elliptic curve that maybe looks something like this, right? And if I have P and Q on this curve and I want to add P and Q, well, here's P, here's Q. As a reminder, you form the line between P and Q. Find the slope of that line. Technically, you need to find it to find the point of intersection. But here, the point of intersection is given right here. Well, get back here. Here, the point of intersection is given right here. There we go. So we call this point R tilde, and then we reflect that about the x-axis to get the actual sum P plus Q. That point right there is P plus Q. And by the way, to prove that this forms a group under this operation of addition, it largely suffices to just look at the graphical process of adding two numbers. Okay. Now let's see why the point at infinity is what we're considering to be the identity element. Let's say I want to find a number let me add a blank page here. I want to find a number, or a point rather, to add to P. I want to find a point to add to P that gives me just P back when I add P to that element, right? Well, if I draw in just a vertical line through, it almost is more convenient to look at sort of what's the opposite of P, what's the additive inverse of P. That's going to be this point of P just reflected about the the x-axis, right? If I draw in that point, and connect those 2 points with a vertical line, you can see that this is going to give me something really weird when if I try to find the sum of P, and let me call this Q for a second. If I try to find the sum of P and Q, that line is never going to intersect the elliptic curve. And so because of this is why we kind of say, oh, okay, let's define this point at infinity that any vertical line goes through. Okay, so this point at infinity is on every vertical line. And here we've seen that if I add P and Q, then I get that point in infinity. So the idea is, well, if I add P to the point at infinity, then what's going to happen? Well, if I add P to the point at infinity, which I think of as being, up here on every vertical line, then P plus that point at infinity, the other intersection with the elliptic curve happens here. And then get the final sum, you flip back to get to P, right? So that is why we define the point at infinity to be the identity element, okay? So that's the only weirdness. And once we define that point at infinity to be the identity element, then you can prove all of the axioms you need to about the group properties for elliptic curves, points on elliptic curves under this operation of addition. Okay. So that's that. Now let's talk about elliptic curves over finite fields. So elliptic curve cryptography is based on the formulas that we developed last time for addition. But instead of thinking of like rational points on an elliptic curve or real points or integer points, whatever, what have you, we're going to view elements of FP as being on this elliptic curve. So we're going to choose a prime number, just like with everything else. Prime numbers you can't get away from them in cryptography. And we're going to look at the points on this elliptic curve that satisfy the equation here, y squared equals x cubed plus ax plus b, but only for points x and y that are elements of FP. Okay. So the only modification we need to make then is, this requirement, this is a requirement here for an elliptic curve that 4a cubed plus 27b squared is not equal to 0. That's for elliptic curves with viewing just the rational points on an elliptic curve. We need to change that now to, if we're viewing this elliptic curve as sort of consisting of points in FP, then I need to modify it to 4a cubed plus 27b squared is not equivalent to 0 mod P. Okay. So for the elliptic curve E given by y squared equals x cubed plus ax plus b, I'm going to call E FP the set of points that satisfy this equation, mod P, with elements x and y from FP. Okay, so what that does is it changes this from being a genuine curve into just kind of looking like random points in the xy plane, which in terms of cryptography, that's what we like. We like things that kind of look random but have structure to them so that we can take advantage of the structure, and so that to everyone else it looks like we're doing something completely random. All right, so how do we add points now that we've gone from the elliptic curve with points being real numbers to the elliptic curve with points defined, points coming from FP? And the answer is we do it using the exact same formulas that we developed last time. So if I want to add the point P, which is x1, y1, and Q, which is x2, y2, on the elliptic curve, y squared equals x cubed plus ax plus b mod P, then I define P plus Q as x3 minus y3, where m is going to be y2 minus y1 over x2 minus x1. X3 is m squared minus x1 minus x2. And y3 is y1 plus that slope times x3 minus x1. Now, all of these operations, the only difference between the last video and this video is that all these operations are done mod p for whatever prime number we're working with. Okay, so really, and I have this on, I think, the next slide. Really, this should say y2 minus y1 times x2 minus x1 inverse mod p. Okay, the other ones, you don't have that weirdness, but the slope, you do need to write that in that way. And don't worry, we're not going to do this by hand. We're going to let, again, basically Python do this. We're going to let a program called Sage do this. Okay. All right, and how do I say double a point? Just like we did last time. So 2 times p, that's the same idea as p plus p. Right, and to get p plus p, that slope, we had to look at. Sorry, that should be a y. The 1 there should be a subscript. There we go. We looked at the slope of the tangent line, which was 3x1 squared plus a all over 2y1, and again, this is going to be done mod p, so this should really be written like 3x1 squared plus a times 2y1 inverse mod p. Okay. And then x3 is m squared minus 2x1, and y3 is y1 plus m times x3 minus x1. And again, as a reminder, the final sum, you do take minus y3 there. You have to do that reflection about the line y equals 0. Okay, and again, these operations are all done mod p. Okay, so as a special note, when I write like that slope, y2 minus y1 over x2 minus x1, really that's just a shorthand for saying m is y2 minus y1 times x2 minus x1 inverse mod p. Okay. However, we're going to let Sage do all of our calculations. Okay, so let me go and show you. I keep talking about this Sage thing. Let me show you this website, Sage. It's sagecell.sagemath.org. So if let me get rid of this here. This is basically one cell of a Python notebook. And so you can do everything we did in Python before. So for I in range 10 print I, for instance, and it spits out those numbers. I can import things that we've imported before. So from simpy import next prime, and I can look at like next prime 9 to the 100, for instance, and it prints out that prime number. And so we can do everything that we've done in Python. But now this gives us the, oopsies, are you sure? No, sorry. Now we can do extra stuff with elliptic curves. So what I'm going to do is I'm going to define an elliptic curve in this cell. So E equals capital elliptic, capital curve. And let's look at an elliptic curve over the FP for P is 7, I don't know, with coefficients 1 and 1. Okay, so what this means is this is the elliptic curve. Y squared equals x to the third plus 1x plus 1. That's what that, and in fact, let me change this to 2, 1, just to make the distinction. Plus 2x plus 1. And this is done mod 7. That's what all these things mean. This GF7 is telling Sage that I want to do all these calculations mod 7. This 2 and 1 are telling Sage that, hey, this is an elliptic curve with a equals 2 and b equals 1. Okay? And so I can do things like look at all the points on this elliptic curve. Okay, there's actually only a finite number of them because FP only has 7 elements, right? So we've got those elements there. This element, if you list the points on any elliptic curve, this will always be listed first. This is how Sage denotes the point at infinity, 0, 1, 0. So this last 0 is just telling you, hey, this is the point at infinity. This is the identity element. All the other elements end with a 1. That's telling you that, hey, these are just normal, normal points on this curve. Okay. So that is how I can look at points on a specific elliptic curve. Okay, and I can change the coefficients and then run this with a shift enter, and so that changes the points on the elliptic curve. If I change this to 0, we get that. If I change this to -1, we get that. And notice for different coefficients, we get a pretty vastly different number of points. So -2, for instance, I can change this to +2, I can change this to 3, and so on and so on. 0. But notice, if I try and do 0, 0, then that 4a cubed plus 27b squared is not 0, isn't satisfied. Let's see what happens. Oh, it gives me an error. It tells me that this elliptic curve over this finite field, that this defines a singular curve, what's known as a singular curve. It has that weird sort of, it's either going to be like a self-intersection or what's known as a cusp in the curve. Okay, so Sage will not let you work with elliptic curves that aren't truly elliptic curves. Okay, but we can get around that by working with actual elliptic curves. So there you go. There's all the points on the elliptic curve. Y squared equals, let me go back to the original example, x cubed plus 2x plus 1. There's all those points, 1, 2, 3, 4, 5. 5 points, which is less than 7, by the way. But again, notice if I change this to 3, 1, 2, 3, 4, 5, 6, that changes to 6. Change that to 5, maybe. We get an error, so a singular curve. If I change that to 4, I get, there we go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points on this curve. So there's not, just from knowing P, there's not really any way to know ahead of time exactly how many points are going to be on the elliptic curve in over FP. But it's going to be pretty close to P in general. Okay. So let's talk about the structure of E of FP, so the elliptic curve over FP. It turns out that it will always be generated by at most 2 points. Now, in cryptography, think back to Elgamal, Diffie-Hellman, what we wanted with FP was like primitive roots. That's a single generator of FP under multiplication, right? With elliptic curves, we can have, sometimes elliptic curves are generated by 2 elements. It has to have 2 primitive roots in a sense. So if I go into Sage, let's look at the primitive roots of, in a sense, of this curve that we're looking at right now. Actually, let's go back to the original example. E dot gens. This is how I look at the what's known as the generators of this elliptic curve. Okay. Now this elliptic curve only has 1 generator, and that makes it really nice for cryptography. This is acting like a primitive root, and we can do things with this. The exact same things that we did with with Diffie-Hellman with primitive roots, with Elgamal with primitive roots. Okay, so when an elliptic curve only has 1 generator, that puts us in back in sort of a familiar situation of being able to work with a cyclic group, a truly cyclic group. Let me change this elliptic curve until we get 2 generators. That one is a bad one. It's a singular one. We get single one. What about here? I'm genuinely not sure if there's gonna give me, if it's gonna give me 2 at any point here. Nope. Let me change this to a 3. Let me change this to a 0. There we go. There's an elliptic curve. So the elliptic curve y squared equals x cubed plus 3x mod 7 has two generators. And that doesn't mean that both of these points are primitive roots. What that means is I can get all the points in this elliptic curve by by taking combinations of these 2 points. But any one of them on their own is not enough. It's not sufficient. So to see that, let me call P E of 1, 5. So this tells me that the point 1, 5, again, the 1 just tells me that I'm not looking at the identity element. So the point 1, 5 is a generator, and I'll call Q the point 3, 6. Okay, and let me look at all of the points on E again. Okay, so I'm going to print E dot points. So we've got 1, 2, 3, 4, 5, 6, 7, 8 points. Now, if I look at all the multiples of P, I'm going to show you that that's not enough to generate all of the points on this elliptic curve. So let's look at all. So for I in range, let's just 1, 2, 3, 4, 5, 6, 7, 8. For I in range 8, print I times P. So I'm just looking at all the multiples of P. And when I do that, I get 0, 1. So I get the identity element. That's 0 times P. And then 1, 5, 2, 0, 1, 2. And then I'm back to the identity element, right? So for instance, 2, 0, I never get the point 3, 1 out of P. I never get that point 3, 1. I only get these 3 points. 0, 1, 0. So the identity, 1, 5. 2, 0, and 1, 2. Sorry, I only get those 4 points. Okay. To get the other 4 points, I need to look at I times Q. And technically, even that full list of I times P and I times Q, technically, for some elliptic curves, that still won't give you all of the points on the elliptic curve. You have to then also take all the possible combinations of I times P plus J times Q to see that. However, we're only interested in elliptic curve cryptography for elliptic curves that are generated by a single point, because again, that gives us a cyclic group, and then we can create an analog to Diffie-Hellman, because with the cyclic group, we can have the discrete logarithm problem, and it's actually much harder to solve the discrete logarithm problem for elliptic curves than it is just in FP. Okay, so let me go back to Sage, and let me go back to our opening example, 2-1. And let me look at, again, E.gens to look at all the points so this is the only point that generates this elliptic curve. The elliptic curve over the solving the equation y squared equals x cubed plus 2x plus 1 mod 7. By the way, let's go into our notes and verify that on E. So E is the elliptic curve. Y squared equals x cubed plus 2x plus 1. So E, we're looking at EF7, the elliptic curve over F7. Let's verify that 0, 6 is even on the elliptic, is even on the elliptic curve, right? Is in EF7. Well, to verify that, I'm just going to plug in this point, the x coordinate, I'm going to plug in for x's, and the y coordinate for the y's. And if I get something that's true, then that's a verification that this point lives on this curve. Okay, so I plug in x equals 0. I get 0 cubed plus 2 times 0 plus 1. Is that equal to, question mark, 6 squared mod 7? Well, let's see. I get 1 on the left, 36 on the right, and that's 1 more than 35. Why, yes, this is satisfied. So that point 0.6 is on this elliptic curve. Okay, so to verify a point is on the elliptic curve is as straightforward as plugging in the x's and y's and making sure the equation's satisfied. Now, verifying 0.6 is a generator, we're going to let Sage do, I'm going to call P that point 0, 6. Sorry, E, you have to do E 0, 6. This is telling Sage I want the point 0, 6 on the elliptic curve E. And then we're going to say for I in range, I think there was 5 points on this elliptic curve, print I times P. Okay. And we get the points 0, 1, 0, 0, 6. So this is the identity. This is the original point P. This is 2 times P. This is 3 times P. And this is 4 times P. So let's look at print E dot points. And we got original 0. Oh, sorry. This is not the identity. This is genuinely the point 0, 1, right? So did we get every single point available? Well, identity, yes. And then the point 0, 1, yes. 0, 6 is our generator. 1, 2, yes. And 1, 5. So the point 0, 6 did indeed generate all of the points on this elliptic curve, which is pretty cool. Okay. Now let's talk about adding points on the elliptic curve FP, E of FP for certain primes. Okay, so if I go back into the notes, let's let E be this elliptic curve y squared equals x cubed plus 2x plus 3. We want to find a generator of the elliptic curve over F19, and then we want to know how many points are in EF19. Sorry, that should be a 19 right there. P is 19 for us for this problem. Okay, so everyone pause the video, go to that website, sagecell.sagemath.org, and see if you can figure out what you need to change to get the generators of this elliptic curve. The generator of this elliptic curve. And then once you find that, see if you can recall how you would find how many points there are on this curve. Okay, so hopefully you paused and tried to do it yourself. I'm going to erase this stuff. I'm going to change this to GF19. The G stands for Galois, Galois. If anyone cares, but you don't need to know that here. And then I'm going to change that 1 to a 3 because we're looking at the elliptic curve y squared equals x cubed plus 2x plus 3. Okay, so plus 2x plus 3. Let me change this comment. I mean, I don't have to change this comment, but it's just nice for me. All right, so let's find a generator. Here we go. We have a generator is 1, 14. So I'm just writing that down. P114 is a generator. Okay. And now the question asked was how many points are in the elliptic curve over F19, and generally it's going to be fairly close to the prime number P. It should be fairly close to 19. To check, I can ask Sage for just the list of points. This spits out like a Python list of points. And so I can ask what is the length of E dot points. And it tells me 20, which if you're keeping track is pretty close to 19. So 114 is a generator, and EF19 has 20 points according to Sage. Now, a question you should have at this point is like, hey, how does Sage find these generators? And frankly, I'm not sure, but I do know if we were trying to find these by hand, you would pick X and Y at random and start adding pick that XY point at random and start taking multiples of that point and seeing if you get all of EFP. Okay. And then you should have the question, well, how do I know if I've gotten all of EFP? And the answer is, don't worry about it. In this class, I'm not so interested that you deeply understand the theory behind elliptic curves, because elliptic curves are not a single step up in difficulty from what we've been doing. They're 5 steps up in terms of the theory. However, we can work with Sage to simplify a lot of the calculations that we need to do. Okay, so if anyone's interested in like how do I know how many points ahead of time are on the elliptic curve over FP, or how do I know how to find a generator, your book is a really good resource. And this is also, if anyone's thinking about doing any sort of like research in cryptography, this is a field that's still relatively booming, and you could start looking into what are modern advances in elliptic curve cryptography. All right, let's move on to this next example, which I actually just biffed because I copied something down wrong. So now I'm going to try it again, round 2. So we want to, for that same elliptic curve, which is y squared equals x cubed, scroll up and look at it, Chase, plus 2x plus 3. We want to verify that 1, 5 is on the curve, and this elliptic curve in 5, 9 is as well. So I want you to do that by hand. Plug in that those x and y values into the curve, mod 19, and verify that those points satisfy this equation. And then once you do that, use Sage to find p plus q, and then 2 times p, and then negative p. Okay, so let's verify p. Verify p, which is the point 1, 5. So if I plug in 1, 5, when I plug in x equals 1, I get 1 cubed plus 2 times 1 plus 3. That is the same thing as 6 mod 19. Easy squeezy. And then when I plug in 5, y equals 5, I get 5 squared. That's the same thing as 25, which is the same thing as 6 mod 19. Bingo! Now let's verify Q. Verify Q, which is the point 5, 9. All right, so I plug in x equals 5, and I get 5 cubed plus 2 times 5 plus 3. 5 cubed is 5 squared times 5, so that gives me 6, because 5 squared mod 19 is 6, right? We just did that in the previous step. So 6 times 5 plus 2 times 5 plus 3, mod 19. Mod 19, which is 30 plus 10 plus 3. 30 mod 19 is 11 plus 10 plus 3. 11 plus 10 is 21. Mod 19 gives me 2, so I get 5. So 5 mod 19. Mod 19. Okay. And I'll plug in y equals 9, and I get 9 squared is 81 mod 19. And 81 divided by 19 is 4. 40 plus 36 gives me 76. That gives me indeed that 5 mod 19. So P and Q are indeed both on this curve. Now let's go and add these points and let Sage do all these operations. So we're going to call P the point on the elliptic curve 1, 5, 1, 5, and Q be the point on the elliptic curve 5, 9. And we want to do P plus Q. When we add P plus Q, we get, I'm just writing that down, P plus Q equals 14, 1. I would encourage you to do one time this calculation by hand using the formulas we developed. I know you're probably laughing at me right now, but I would encourage you just to see that you can do it. That is not like, it's a lot of steps, but it's what we've been doing all semester, modular arithmetic. I would encourage you to try it out yourself. Okay, you should get 14, 1. All right, then 2 times P. In Sage, we can do this pretty easily. I can do, so let me go back and do print. Let's print 2 times P. And we get 313. I'm just writing that down. Again, I would encourage you to try this one by hand as well and compare it to the answer using the formulas we have earlier in the slides. And then lastly, print minus P, which that one's is actually kind of hard to do that one by hand. Minus P. It's easy to visualize it on the curve, but it's kind of hard to do this just straight up from the formulas. But minus P is 114. 1 comma 14. Very cool. And we can verify that minus P, let me call that this point R is 1 comma 14. 1 comma 14. And I can verify that P plus R is the identity here, right? Print P plus R. And we get the identity 0, 1, 0. Okay, so there you go. There's how you add points in Sage. Again, we're going to be using this Sage program to talk about elliptic curve cryptography. Next time we'll talk about the discrete logarithm problem for elliptic curves over finite fields. It is as hard as it is to solve over FP. It's even harder to solve over elliptic curves over finite fields, which is why we like it and why a lot of websites nowadays are using elliptic curve cryptography. So we'll talk about the Diffie-Hellman key exchange using elliptic curve cryptography, and then in the final video, we'll talk about actually encrypting using this, using a version of Elgamal. So that's that. Thank you all for your attention. Make sure that you keep practicing this. You can use Sage on the homework, but I would encourage you again to try out at least one computation by hand using the formulas that we looked at in this slideshow. All right, so if you have any questions, feel free to email me, and keep watching these videos and keep practicing in MyOpenMath and getting stuff done. Thank you all. Have a great rest of the day.